Hello, and welcome back. Today we're going to be talking about exponent laws as part of our unit on exponents. So we have a couple of investigations to do this class, right? We'll do a very quick minds-on activity, 2 investigations, and then we'll summarize and do some examples before you go to your practice. In this lesson, you're going to learn 3 different laws of exponents. These laws are called the product law, the quotient law, and the power law. How do you know that you have succeeded at this? Well, when you can determine through an investigation, what are the rules when you are multiplying or dividing expressions that involve exponents? And what are the rules when you are simplifying a power of a power? To get our minds in the right groove, just a very simple question here. Write this in expanded form. Take a second to do that. Well, hopefully you realize that this is 4 multiplied by itself 3 times. So that's how I would write this part, right? That's how I would expand this power. 4 multiplied by itself 3 times. And then I have to multiply, so I'll put another multiplication symbol here, by 4 to the power of 5. And what is 4 to the power of 5? That's 4 multiplied by itself 5 times. And so in total, I have 4 times 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 4. That is the same thing as if I wanted to write this as a single power, what would be the same way of writing 4 times 4 times 4? 4 multiplied by itself 8 times. That would be 4 to the power of 8. The same number multiplied by itself 8 times. Taking a look at this, what do you notice? Any coincidences? Think about this for just half a minute. Well, it's pretty easy to notice that if we have 3 of these here and we have 5 of these here, then altogether we got 8. And how did we get 8? By adding 3 plus 5. 3 of these plus 5 of these got us 8. So this is actually an example of something called the product law of exponents. And mathematicians have invented this or discovered this because they were like, I don't want to write it in expanded form every single time. I want a way to look at something like this and simplify it. And this is what the product law they came up with is. When you have 2 powers that are being multiplied, that's why it's called the product law, right? The answer to a multiplication question is a product. The product of 2 powers with the same base, notice that this only works if this is 4 and 4. If this was 4 times 4 times 4 times 5 times 5 times 5 times 5 times 5, then this would not work. Instead, they need to have the same base. Then to find out what the product is, you can just keep the base the same. This is a to the power of b. So a multiplied by itself, b times. And this is we're multiplying that by a to the power of c. So that's a multiplied by itself, c times. How many times are we multiplying a by itself altogether here? It's always going to be this number plus this number. So b plus c times in total. And the way we write that as a single power is a to the power of b plus c. So if I wanted to do 4 to the power of 3 times 4 to the power of 5, I could skip right ahead to this step just by adding 3 plus 5. In fact, this even extends to when there's more than just 2 powers. If there was another power of a, we could even add that exponent in here. Okay, so this, whenever you're multiplying any number of exponents, that as long as they have the same base, that part is important, you can always add their exponents together. Now that we're all warmed up, let's start our first investigation for the day. So here I will ask you to simplify this expression and then evaluate it. And just take 1 minute to do that. At first glance, you might say to yourself, oh, I'll multiply all of these and then divide it by 3. That's true. You could do that, okay? But I'm going to work at this a slightly different way to show you that there's another way to think about this that will help us later. The first thing I'm going to do is recognize that I could probably, if I'm multiplying by 3 and then dividing by 3, what's going to happen there? Imagine you have $5. Times 3 is 15, divided by 3 is right back down to 5. Any number multiplied by something and divided by that same thing will lead you right back to the same spot. So I could cancel out these 3's, but then what would be left in the denominator? A lot of students think that it would actually be 0 in the denominator, and we're never allowed to divide by 0. But I would say that if we're looking at this as multiplication, another way I could write this, the denominator is 1 times 3. And when I'm looking at it like this, now if I cancel out these 3's, I'm left with 4 times 3 over 1. The truth is, I didn't really have to write times 1 here. If I canceled it out in this step here, if I just did this, if I just canceled out these 3's, I would still end up in this position. But because the 1 is not appearing here, some students get confused and they think it's actually 0, but it's not. We can see through this example that there's actually a 1 being multiplied by everything. And now that I have this, I can do 4 times 3, which is 12, and 12 divided by 1 is just 12. In fact, anything over 1 is just itself, right? Anything divided by 1 is always itself. So at this point, I could have just done 4 times 3. Now, why did I do this instead of going 4 times 3 times 3 divided by 3? Well, 4 times 3 is 12. 12 times 3, ooh, that's a little bit harder, 36. And then divided by 3 would still get me 12. But that's a little bit harder to do, right? The numbers got really big, and then we made them small. Whereas if we simplify first, we're keeping the numbers in sort of a more manageable situation. Now let's get to this portion right here. Write this in its expanded form, and then try to write it as a single power. Take 2 minutes to try that out. Well, here we have 4 to the power of 5. What does that mean? That means we're taking the number 4 and we're multiplying it by itself 5 times. So that is 4 times 4 times 4 times 4 times 4, a total of 5 times. And then we're dividing, right? So instead of writing this as the division symbol, what I'm going to do is write it as a fraction, right? A numerator and a denominator, just like we have here. These mean that you divide. So I'm going to divide this, and what will my denominator be? In this case, I'm dividing by 4 to the power of 3, and 4 to the power of 3 means I'm taking 4, and I'm multiplying it by itself 3 times. So this is the expanded form of 4 to the power of 5 divided by 4 to the power of 3. Let's write this now as a single power. Take a minute to see if you can do that. Remember, looking back here, there may be some way that you could simplify it. I'm not asking you to evaluate it. I'm not asking you what is the number that represents all of this. I'm asking you to write it as a power. And you can use the previous exercise as a clue. To write this as a single power, notice that just like we did over here, because we were multiplying by 3 and then dividing by 3, we were able to cancel those out. We're going to do something similar here. I'm going to cancel out because I'm multiplying by 4 and dividing by 4. I can cancel those out. And in fact, I could do that again over here. These two will cancel out as well. And so will these two. So what will be left here? In the numerator, I will have 4 times 4. In the denominator, will I have 0? No. Just like we saw here, we are going to be left with 1. So how could I write this as a single power? This is just 4 to the power of 2, because we're multiplying 4 by itself just 2 times. So I'd like you to take this idea and really run with it. Okay, copy down this table and try to complete it. And all you're going to be doing is really repeating these steps. And once you're done the entire table, ask yourself this question: what do I notice? So in this investigation, we're just going to fill out this table here. The first row has this expression, 9 to the power of 4. And how do I write that in expanded form? That's 9 multiplied by itself 4 times, then divided by, so I'll put the line under it to indicate that it's sort of like a fraction. And then I'll put 9 to the power of 2, which is 9 times itself 2 times. What's going to happen here? When we're multiplying by 9 and dividing by 9, the same way that we did up here, these two will cancel out, and so will these two, and we'll be left with just 9 times 9 on the top and 1 on the bottom, right? This is all times 1, just like we did over here. And this, as a single power, the way we write this is simply 9 to the power of 2. Our next row here is 6 to the power of 5 divided by 6 to the power of 3. This is 6 multiplied by itself 5 times, divided by, this means the same thing as this division symbol, 6 multiplied by itself 3 times. These will start canceling each other out. And once we run out of 6's to cancel out, because we've run out of 6's on the bottom here, we're left with just 2 on the top, and that would just be 6 to the power of 2. The third row, what happens if the base is a negative number? What does this look like? This is negative 5 in brackets multiplied by itself 6 times. And then we divide that by negative 5 multiplied by itself 2 times. Then we do our cancellation. And we are left with what? Now it's no longer, negative 5 to the power of 2. Now we have negative 5 times itself 4 times. So if you were looking at this and saying, I will always end up with 2, we can see that that's not the case. Here we're left with 4. And finally, over here at the bottom, this last row, a negative fraction is our base. Does that change things? Does that make things different for us? No. This still says take this base and multiply it by itself 5 times and divide that by that same base multiplied by itself 2 times. And again, we do our cancellations. Now, only 2 of them will cancel out. Similar to this one, only 2 will cancel out. Over here, we had 3 canceling out, and we're left with just 3 negative 1 over 3's on the top. What does that mean? That this is negative 1 over 3 to the power of 3. And so that number, even though we canceled out 2, just like we canceled it here, is not the same as this 4 here. What is actually happening here? What do we notice? One thing you might notice is that the bottom numbers, because we are multiplying by the same number on the top and the bottom, because these powers both have the same base, we can do these cancellations. That's what allowed it to happen. And so the bottom numbers always canceled out the same number of them on the top, right? We had 3 6's here, we canceled 3 6's on the top. What did that mean in terms of our expressing of this as a single power? See if you notice anything here. And if you're looking really closely, you might notice that over here we had 4 9's, and here we had 2. So if we're removing 2 from the top here, we can always take 4 and subtract 2 of them, and that would give us 2 9's left over. Over here, we had 5 6's at the top and 3 at the bottom. So we can take, and if we're removing 3 from the top, because that's how many will cancel out, well, won't we always end up doing 5 minus 3 to get 2 as well? Doesn't this number represent, how many are left over after we cancel them out? Over here, how did we end up with 4? We can see that same pattern, right? We started with 6, we canceled out 2 from the bottom, and that left us with 4. And finally, when we started with 5 and removed 2, that left us with just 3 of this number being multiplied by itself. Now let's take this and see if we can come up with the actual rule for it, although I think that, it should be pretty easy from here, right? What is a to the power of b divided by a to the power of c? Can we write that in its expanded form? And then can we write that as a single power? Take 2 minutes here to see if you can write down both of these. This might be a little bit tricky because, you don't have numbers here. I didn't give you numbers. But we're going to treat this almost as if we had numbers, just like we did in the investigation. Over here, we have a to the power of b. That means, just like when we had numbers, when it told us to take the base and multiply it by itself this many times. So notice the way I drew it. A times ... to indicate that there are a bunch more a's in here. How many? I don't know. But I'll keep multiplying it by a, by a, by a, and then again, there's a bunch more in here, times a at the end. Altogether, how many times am I multiplying a by itself? B. Again, I don't know what number this is, but this is sort of a representation of what a to the power of b might look like. Similarly, now I'll divide by a to the power of c, and a to the power of c could be something like this: a times, and there's a bunch of a's in here, times a. Altogether, I'm multiplying a by itself c times. B and c could actually be the same number. They could both be 5 and 5. I haven't really said how many a's are inside here or inside here, but this is just a representation to understand what is actually going to happen when we divide these. It might appear that I have at least 4 a's in the numerator and just 2 a's in the denominator. That's not true. That is just my representation of it. Okay? I'm actually saying I don't know how many a's are up here. But if there were a bunch, this is kind of what it would look like. If I skipped over a lot of them here and a lot of them here, and if I skipped over a lot of them here. In fact, a to the power of b, if b was just 2, then there could just be 2 a's on top. Okay? It doesn't matter because what I'm doing here is I'm using this to understand the idea of what's actually going to happen, just like we saw in our investigation. And what is going to happen? In our investigation, the a's in the denominator, or whatever the number is in the denominator, each of those canceled out 1 from the numerator. So if I have 5 of them here, 5 will cancel out from the numerator. So all of these will cancel out the same amount from the top. How many were removed from the top? How many a's were removed? C. Whatever was from the bottom. And therefore, how many a's are remaining here? Although it may seem like half of b, how many a's are here? Half of whatever this number is. That's just my representation. So there could have been 5 a's here, and there could be 20 a's over here. I'm not really saying how many are in the middle of these dots, but I do know that if I started off with b a's, and I removed c a's, what is an expression that I could use to represent what's left over? B minus c. I started off with b, and I subtracted c. That leaves me with b minus c. And so if I want to write this as a single power, it would end up being a times itself, b minus c times, which is just a to the power of b minus c. So our first little summary here is that when you're doing operations with powers that have the same base, one thing you can do is you can use some tricks to simplify what your expression is before you start actually solving it so your numbers don't get too big. The product law of exponents is the first thing we learned in this lesson. a to the power of b multiplied by a to the power of c tells you that if the bases are the same, you can just add the exponents together. And just now we finished learning the quotient law of exponents, which is when you're dividing powers that have the same base, you keep the base the same and you subtract the exponents. We have one more investigation to do as part of this lesson. So I'll ask you to take a minute here, pause, and answer this question. Write this in its expanded form, and then write it as a single power. So this would look like, one way to look at this is to pretend that everything in the brackets is a base by itself. I know it is a power, and so this investigation will help us recognize what's going to happen when the base of our power is in blue, when the base, which is in orange, is a power itself. The first thing we're going to do is treat it just like a number. Okay? This is just, 7 squared. And we're multiplying it by itself 3 times. So we're doing 7 squared times 7 squared times 7 squared. And each of these is also a power, so I could start representing this, in expanded form again. I can say 7 squared is 7 times 7, 7 times itself 2 times, just like that. And I can then multiply that by 7 times 7, 2 times. Then multiply that by 7 times itself another 2 times. In total, how many 7s do I have? Well, I have 3 groups of 2 7s, and 3 times 2, which means I have 6 7s in total. I'm multiplying 7 by itself 6 times. So as a single power, I can say that this is 7 to the power of 6. So we're going to do another investigation now, and I'll say it should take you just about 10 minutes to finish this investigation. Fill out the table, repeat the same steps that we looked at over here, and then again at the end ask yourself, what do you notice? So let's just take this up now. In this first row, hopefully you got a chance to complete this entire table. In the first row, 9 to the power of 4 all squared. Well, we have 9 to the power of 4, and we're multiplying that by itself 2 times. So what we have here is 9 to the power of 4 times itself 2 times, and then 9 to the power of 4 itself can be split up into 9 times 9 times 9 times 9, multiplied by 9 times 9 times 9 times 9 again. 4 times each. And in total, because this is 4 times each, in total, how many 9s do we have? If I want to write this as a single power, this would be 9 to the power of 8. Our second row here is 6 to the power of 3, and multiply that by itself 5 times. Each of these powers is actually represented by 6 times 6 times 6. 6 multiplied by itself 3 times. Each of these is being multiplied, and each one is 6 times 6 times 6. Okay, so we're multiplying 6 by itself 3 times in each of these 5 groups. And in total, how many do we have? Well, if we have 5 groups of 3, that would be a total of 15 6s. In our third row, we start to look at what happens if the base is a negative number. This would be negative 5, all in brackets. Remember, we have to keep this, because this is a negative number, we do need to keep it in brackets. This is negative 5 squared times negative 5 squared times negative 5 squared, a total of 3 times. And then when we multiply it by itself twice, right, each of these is negative 5 times itself twice. So we have 3 groups, and each group has 2 negative 5s. In total, we must have 6 negative 5s. Now this is not equal This is not the same thing as negative 5 to the power of 6. And if you don't believe me, you can try to punch each of these into your calculator, and you'll see that this number gives you 15,625, whereas this number gives you negative 15,625. Why might that be? The reason is basically because of order of operations. Remember, we always take the exponent before we multiply, and this is sort of like saying take the negative of 5 to the power of 6. In other words, negative 1 times 5 to the power of 6. Okay? I'm not sure why it's written this way exactly. Who knows if there's a better way to write it that's less confusing. But this is just the way it is, and so we have to be careful about that, okay? When we're multiplying a negative, we just have to make sure we keep that negative base in brackets. Finally, what happens if our base is a fraction? Nothing really different. This is negative 1 over 3 squared times itself 2 times, just like that. And each of these has 2 groups. So we multiply it by itself. A total of 2 groups of 2 is 4 times. The last question that we have to ask ourselves here is, what do you notice? What is the pattern? What did we repeatedly do every single time? If you look very carefully, you'll notice that if we had 2 groups of 4, that got us 8. 2 times 4 got us 8, right? 2 groups of 4, in total that's 8. 3 groups of 5 also got us 15. And it seems like we were doing this every single time. We were always taking the exponents and we are multiplying them, because when in our expanded form we have groups of powers. And over here as well, 2 times 2 would get us 4. So let's see if we can summarize this as a rule. Write this in its expanded form, a to the power of b, all to the power of c. And then can we write this as a single power? A to the power of b, we're going to treat this like a number itself, and we're going to multiply it by itself c times. And then each of these is a multiplied by itself b times, just like that. Multiplied by a multiplied by itself another b times. Multiplied, and then we keep going. I'm not sure how many of these there actually are, but each group is the same size. Each group will end up being the same size. We have B groups. Sorry, we have, how many of these do we have? We have C groups, and each group has a size of B. So in total, we're multiplying A by itself, BC times, B times C. And that would give us as a single power A to the power of, how many times are we multiplying A by itself? BC times. This is something called the power law of exponents. So the third law that we've learned today is the power law of exponents. When you have a power of a power, simply multiply their exponents together to simplify that. There's one more law that I'll ask you to keep in mind as you go through this topic and as you encounter it more and more, and that is the power of a product of exponents. So just going back a second, the power law of exponents is when the base of a power is a power by itself. You multiply those two. But what if the base of a power is a product of 2 different powers? Well, very similar to the distributive property, what this means is you're taking a to the b multiplied by itself c times, and d to the e multiplied by itself c times. In other words, you would have something like a, b, d, e times a, b, d, e times, and so on and so forth. But if we collect all the a, b's, we'll have c number of those. If you collect all the DEs, we'll have C number of those as well. So we can just sort of take this exponent on the outside and multiply it by each of the exponents on the inside. Let's take a look at some examples. To simplify this expression, I'm going to use the power law of exponents because I'm multiplying powers that all have the same base, x. And when I'm doing that, I can just add their exponents together. So they all have the same base, so I can just say 2 plus 3 plus negative 2 is going to be their exponents. 2 plus 3 plus negative 2. And that just leaves me with 3. So the end result here is x to the power of 3. In the second example, not only are we multiplying, but now we're also dividing. So I will use the quotient law of exponents as well. So in this case, I have the same base. So when I'm multiplying, I can add these two together. So I'll have the exponent will be 2 plus 3. And then I have to subtract this third exponent. So I'm subtracting negative 2. And that gives me x to the power of 7. 2 plus 3 is 5. 5 minus negative 2 is 7. In this third example, not only do I have multiplication happening here, but I have a power of that as well. So in this case, I'm going to try two strategies. The first one is to use the power law of exponents. But to do that, I need a single power down here. Can I simplify this to become just one power? Yes. These two powers have the same base, which means I can use the product law to add their exponents together, and 2 plus 3 is 5. And now I'm in the situation where I have a power to the exponent of yet another number. So in this case, I can multiply the two exponents, and 5 times negative 2 is negative 10. The other strategy I'll use is instead of combining these first, I can instead use the product of exponents rule, where I can take this outer exponent and multiply it first by 2. So 2 times negative 2. And then I can multiply this result by 2 times 3, by x to the power of 3 times, negative 2. So I've multiplied these two together, and I've multiplied these two together now. And this ends up being 2 times negative 2 is negative 4, 3 times negative 2 is negative 6. And now I can use the product law to add these two exponents. And of course, negative 6 plus negative 4 is negative 10. And this is exactly what I got in the previous example. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.